So here's the deal. We are done with the stuff that I'm planning to give you any new problems on, test on, anything like that. We're done. So no new problems. So the first thing is that means that every day until we're done, I'll answer any questions that you have. If you bring homework questions, test questions, you want to see anything like that, I'll work on those. But there's always more stuff to go into, and I thought I'd give some introductions to some things that are sometimes taught in this class that are sort of cool things that can come up in the future. Yeah, right. Yes. Yeah. For fluid dynamics, I could probably talk a little bit about fluid dynamics, but definitely I can't do that today. But I'll look into that. Yeah. Some random fluids out of my ass. Okay. Okay, sure, I'll do that. Today, right, not the ladder. Okay, so now we're into the section of this class that I like to call a few intros. Well, one, yeah, I could do that right now. It would take you it would take you 40 hours to solve, but. And then go over. Okay. Well, the first one, okay, so that would be very easy to do after this first thing that I want to talk about. So the first thing I want to talk about is internal loads in structures. And so, you first think about it. I mean, we did internal loads in a couple of structures. So, yeah, what's hard about that? Well, actually, it's not really like hard, but what you do get is that when, so you have a member that's at an angle, and on that, if it has weight, you have a distributed load that's not perpendicular to the member. So when you use a rotation matrix to think of the thing as being flat, really what you do is use a rotation matrix so that the positive x-axis goes along the long axis of the beam. You have a distributed load that has an x and a y component. And we haven't talked about that. So I want to talk about that because then you can do any kind of structure, re-express it in a new coordinate system, and find the internal loads. And then once you find the internal loads, you can get into everything else that we've done in this class, talk about, you can do statically indeterminate systems, you can calculate the stresses, all that kind of stuff. So that's the first thing. The second thing I want to talk about is pressure vessels. Brew beer? I don't know how to do that. That would be, I wish I did. I know how to calculate the stress in the, yeah. And so, yeah, what kind of stresses are there in the, if you have a spherical or a cylindrical thing with a pressure inside as the main load, how do you calculate the stresses and the strains, figure out, if you're in danger of this thing blowing apart, So we'll talk about that. And then I was going to talk about strain energy. None of this is going to take too long, I don't think. So, but let's do fluids instead, because, you know, that's at least as useful. So talk about fluids. Let's do that. And that should get us about to the end. And you can think of this as all just like, this is just something to store in the back of your head. I'm not going to assign any problems based on this. The only problems that I'm still going to assign are redoing problems that you've already done, just trying to solidify stuff. Okay. Any questions? Yes. 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 Oh, right. I still haven't assigned all the, I'll still assign more column problems, a couple more column problems. But I'm not going to do any more in class. I just haven't written those yet. So. Ooh. Let me think about that. Yeah, I'm sure that's probably, we could probably do something like that. Is this the class that has the 8 a.m. Friday? That's dynamics. Okay. It's dynamics that has the, okay. Let me think about that. Okay, so so the first thing is internal loads and structures. Okay, so let's imagine that, for example, you have something like this. You have some external load applied. And let's say that masses are, we'll say that's 2 meters long, and that the masses of each of these are 50 kilograms. Yep. And I don't know what this angle, let's say that's 30 degrees. What are the internal loads in each of these beams? Well, the main issue is the distributed load. Right now, we know how to deal with everything except everything that would come up in a problem like this, except the distributed load representing the weight. It is spelled weight with a G. Okay. And so we would get something like this for the left member. You know, free body diagram of, let's call this member 1. we have a force here, a vector that's the force on 1 by 2. And we have a force vector down here that I'll call that RA. And then we'd have that 1,000 Newton force this way. And none of that's hard to deal with. The thing that can be a little confusing that we haven't talked about yet is the weight shows up as a distributed load like this that's equal to the total weight force is 50 times 9.81. So the total weight is 490.5 newtons. And then as a distributed load, it's 490.5 divided by 2 meters. So you get 245.25 newtons per meter. That's the distributed load. Okay, well now we want to go from these values are in a coordinate system like this, right? And we want to re-express everything in a coordinate system with the x-axis along the beam. So we want something like this. What's the rotation matrix that we need to go from that coordinate system on the left to the one on the right? It's 30, but yes, positive 30. And then about what axis? Z-axis, yep. So theta is equal to positive 30 degrees about Z. And you can think of that distributed load as a vector. So we'll take this rotation matrix that's cosine of 30 is 0.866. Sine of 30 is 0.50. Negative 0.5. Positive 0.866. 0. 0, 0, 1. And in the original coordinate system, what's that distributed load vector? Yep, 0. Negative 245.25. 0. That's the distributed load vector in the original coordinate system. And so what do you get when you multiply those two? Well, the first one is half of that. Maybe I can do that. That's negative 1, 2, 1, 2, 2, 122.625. 0.393 and then 0. And the units here, this is newtons per meter. That's a distributed load. Okay, so now, after you do that coordinate system transformation, we have two components to the distributed load. We have a horizontal component that's going this way with a magnitude of 122.625. And we have a vertical component that's down with a magnitude of 212.393. Bless you. And then we have these things, you know, I'll call this RA in the new coordinate system and some other F the new coordinate system. We'll come back and do a problem where we deal with those. The RA new or the okay. Well, so these are both uniform distributed loads, and so let's think about what that what happens. This horizontal distributed load is acting right along the length. And so when we do a cut, we're going to have a piece that has a length of x. We have this force vector over here that's RA new. And then that uniform distributed load, the horizontal one, now that we've chosen our body to isolate, we can represent that as a point force. Okay. And what's the magnitude of that point force going to be? Yep, exactly. 122.625x. And then we can represent the vertical component as a point force. What's that going to be? Yeah, 212.393x. And then we have our internal loads. And this point force is acting along the center line, horizontal, pointing towards the left. So when we add up the moments about the end, what's the moment going to be that's produced by this force? Nothing. Its line of action goes right through the about point. And so this will factor into the Newton's second law when we add up the forces, but it's not going to show up in the moments. Everything else is just the way that it's always been. So this is going to be the first time that we've ever seen the internal tension show up as a function of x. We've never seen that because up until now we've only dealt with horizontal point forces, and so we've just had these constant values. So this produces, it's a force. But no moment. Yep. Rotated. Yeah, might as well. We don't remember that the answers we really end up getting for all this stuff are like principal stresses and maximum shear stresses, and those are all in their own coordinate systems anyways. So yeah, might as well just keep it here. Okay, so let's go through this whole problem and just see how this works. Okay, so the first thing we're going to do is isolate the individual bodies. So I'm going to call this one body 1, this is body 2, and these joints are A, B, C. And so on body 1, we have this force vector RA, a force vector F12, a horizontal force of 1,000 newtons, And now that we've chosen the body to isolate, we can represent the weight of that body as a point force. So it's right at the center with a magnitude of 490.5. Since this one's at an angle, let's draw out rho, force, and moment. All right, so for the force RA, let's choose that as the about point. So that force RA has no rho vector. The force is RAX, RAY, and there's no moment. And next is the weight force. The rho vector, the length of the whole thing is 2 meters. So the distance from here to here is 1 meter. So that's 1 times cosine and sine of 30 degrees. So that's 0.866.5. And the force vector is 0, negative 490.5. And what's the cross product? Negative 424.773. Oh, thank you. I was hoping you'd let me. And then at the top, I guess, well, no, I'll keep it as 2 separate forces. So force F12, that has a rho vector of 1.7321. The force vector is F12x, F12y. And the cross product is 1.732 F12y minus F12x. And then the last one is that 1,000 Newton force. That has the same rho vector as F12, 1.7321. The force vector is 1,000, 0. And so the cross product is negative 1,000. Add up all the forces in the force column and set it equal to 0. Your first 2 equations are from Newton's second law. RAX plus F12x is equal to negative 1,000. Stop me if you have any questions. That's from the x component of Newton's second law. The second equation says RAY plus F12y is equal to positive 490.5. And then the third equation comes from setting the moments equal to 0. That says negative F12x plus 1.732 F12y is equal to positive 1,424.77. Any questions about that? The first 3 equations? And now the free body diagram of the second one. Over here we have RC. Over here we have negative force on 1/2. You can't So we've already applied that 1,000 Newton force. You can't do it on two bodies, so I'm going to leave it off here. And then the weight force, since we've chosen the body to isolate, we can treat that as a point force. And so that's a downward force of 490.5. And then rho, force, moment. Let's see. I guess I will go, let's put the about point here. What? Oh, for this isn't, yeah, it's not dynamic. You know, that for a linkage, you're right. This thing is stable, you know. And so if it's at rest, you can choose any point in the universe you want as the about point, because every point is a fixed point if it's not able to move, you know. So F12, row vector is 0, 0. Force vector is negative F12x, negative F12y, and 0 cross product. Then the weight force, that row vector is positive 0.866, negative 0.5. The force vector is 0, negative 490.5. And the cross product is negative 424.77. 424. That's what it was before. And then the force RC, the row vector is 1.732, negative 1. Force vector is RCX, RCY. And the cross product is 1.732 RCY plus RCX. So now our fourth equation in our system, add up all the x components of the forces and set them equal to 0. So you get negative F12x plus RCX is equal to 0. Add up all the y components of forces and set them equal to 0. And that says negative F12y plus RCY is equal to positive 490.5. And then add up all the moments and set them equal to 0. So we have 1 RCX plus 1.732 RCY is equal to positive 424.77. So that's 6 equations. We have 6 variables, F12, RA, and RC. Those are all vectors. Anybody been solving this whole time? Yeah. Mm-hmm.
C is negative 94.77 and 779.
Sorry, did you say, so this is negative 924.77? Okay. And then Y? 779.18. Does that make sense? Maybe. Did you get the same thing? No. Oh, okay. Can a couple people, can someone else do that? I feel like I expected symmetry. All right. Well, now, before we go into the internal loads, let's just be really clear about what we have. So, on this body over here, we have the force RA at the bottom that is a force vector of negative 75.23, 201.82. And up at the top, let's add those. There's two force vectors acting on this body at the top. Let's add them both together. There's this force vector, F12, and then a force in the positive x direction of 1,000. So I think that comes out to be positive 75, well, yeah, it has to be, 0.23, and then positive 288.68. And then there's also the weight. And the weight is a downward distributed load. With a magnitude of, well, let's write it as a distributed load. So it's 490.5 divided by 2 meters. So 225.25, 245.25. Yeah. Newtons per meter. And then on the other one, right hand, we have this RC, a negative 924.77, 779.18. And then up at the top, we have negative F12. So that's positive 924.77, negative 288.68. And then we have the distributed load representing the weight. Which is 245.25 newtons per meter. That's what?
The other one's 0.2.
Mm-hmm.
Oh, yeah.
That's right. So they're not because of that 1,000 Newton force. So, and the cool thing is, if I know the people who didn't take statics from me did these calculations in a different way. But the sort of weird thing is we just arbitrarily said the 1,000 Newton force is acting on this body. But if we had arbitrarily said that 1,000 Newton force was acting on this body, we would have gotten different values for F12, but when we added everything together, we would have gotten exactly the same free body diagrams at the end. Like it works itself out. It feels like magic. Yeah, probably. Well, wow, who would have guessed? Like this thing is really screwed compared to this one. I didn't expect that, but I guess now that I think about it, it sort of makes sense. That's right. Yeah, like the weight's trying to compress this, and that other force is trying to compress this one. It's trying to stretch this one. Interesting. Okay.
Is the weight affecting from the left one affecting the right one because it's pushing over that? Probably a little bit.
Yeah, a little bit. Yep. Not compared to the 1,000, right? Okay, so now what we're going to do, so now, so far we haven't done anything that at least the people who took statics from me haven't done. You know, we've done problems like this in here. Now we're going to go from, so let's start with body one. And right now all of our vectors are in this coordinate system. But we want to switch it so that our coordinate system is like this. So that means using a rotation matrix that's rotated positive 30 degrees about the z-axis. Okay, so first we'll do that with, so we have 0.866, 0.5, 0, negative 0.5, 0.866, 0, 0, 0, 1, and first we'll multiply it by this force RA. So that vector is negative 75.23, 201.82, and then there's no z. So what we're getting now is RA expressed in the new coordinate system. And could you tell me that when you get it? Okay. Okay, and then 0z. So this is RA in the new coordinate system. And now we'll take the same matrix and multiply it by the force vector up at the top, that combined force vector. So that's 75.23, and then 288.68, and then 0. Can you calculate that? Okay. Okay, 0. That's the top force vector in the new coordinate system. And then the distributed load, we already did this one. So that distributed load is 0, negative 220, 0, negative 245.25, 0. What's that? Okay. 4, 0, and then 0. And this is newtons per meter. I didn't write the units on the other one, but we have to remember that this is a distributed load vector. So this is the distributed load in the new coordinate system. Okay, so now we have a beam that's this way and a coordinate system that's rotated with the x-axis along the beam. For internal loads, we want the beam flat and the coordinate system flat, so what do we have to do to... Yeah, exactly. That's what I was looking for one of you guys who took my class to say, turn your head a little bit. But yeah, right. So all that matters is the relationship between the body and the coordinate system. Now we have what we want, even though everything's really tilted, you know. So now we're here. I'm drawing it bigger so it doesn't all look too compressed, but the left, okay, so the left force vector, 35.76, .40. Right vector, 209.50, 212.39. I'm going to call that round off error. And then the distributed load, I'm going to write that as two different components. A horizontal component in the negative x direction of 122.63. And a vertical component down. This is newtons per meter. And this downward force, this downward distributed load is 212.40 newtons per meter. And now we're ready to do the internal loads. How many cuts do we have to make? Yeah, just one. So just anywhere between the endpoints, because those distributed load functions don't change anywhere. So cut 1 is valid for any x between 0 and 2. We have the force vector over here of 35.76 to 12.40. Now that we've chosen the body to isolate, we can represent both of these as point forces. So let's see, I'll draw the horizontal one like that, and it has a value of 122.63 times x, because that's a uniform distributed load. And then we have the downward force that's equal to 212.40 times x. And then the internal loads, T, V, and M. Newton's second law says 35.76, 212.40 plus, I'll put these all in a single vector. We have negative 122.63x and negative 212.40x plus T negative V is equal to zeros. So the internal tension is positive 122.63x minus 35.76. And the internal shear force is negative 212.40x plus 212.40. Okay, so here for the first time, we have a value that changes for the internal tension. We have a value that changes continuously as you go along the beam. If you're all the way at the left end, x is equal to 0, and you have a 35.76 is the tension there. It's in compression there. But once you get to whatever, at some point here, it crosses over. Somewhere in there, you have 0 tension. There's one spot. And then from then on, as you go farther this way, at every point, you have a bigger value of tension. It switches from compression to tension continuously. Cool, right? And then the moment equation. The about point, we'll do it the same way with the about point at the left. So that force vector at the left doesn't do anything. The horizontal force from the distributed load doesn't do anything, but the vertical one does. And it has a moment arm of x over 2, and it's clockwise. And then plus m minus Vx is equal to 0. So m is equal to so Vx plus 106.20 x squared. And so m is equal to negative 106.20 x squared plus 212.40 x. The derivative test works. dm dx is equal to v. dv dx is equal to negative q. Q is a downward distributed load. I hope. Yeah, negative 212. And now there's this new one that maybe if you're like following, if this is making sense so far, you can imagine that there's a new derivative rule that never mattered to us before. But dt dx has to be equal to the distributed load function, the horizontal distributed load function. So take the derivative of that, you get 122.63, and with the signs, you can decide what sign convention you want. And so now we have the internal loads for this beam that was originally in this structure. And now we can go through and calculate the stresses and whatever and see in this structure, in that configuration, where are the places where we're concerned about, what you'd probably want to do is calculate the principal stresses, then calculate the maximum shear stresses, and where that's high, we're concerned about this thing breaking. I think I'll probably next time, well, maybe either I'll go through it or I'll give you time to go through it and then I'll go through it. But we'll just go through the other piece and see what it looks like. Since the other piece, it turned out, was the one that's in more danger of breaking, it looks like anyways. Any questions right now? Okay.